So coming up next are not one, but two speakers, so I have to use this hand mic thingy to introduce them. Please welcome Daniel from Omega Point and Akka Made Our Day.
Thank you. Thank you. See if the remote works. Yes. And everybody can hear me? Thank you all for coming. And I'm glad you made it, and I'm glad to be here. My name is DanielSawano, and this here is my colleague, Daniel Deogun. And we both work at a consultancy company called Omega Point, which are based here in Stockholm, and we have offices in Gothenburg, in Malmö, and New York, and a couple of other cities. And we basically do what most people do. We help our clients build great software. So, a little bit about what we will be talking about today is we will give a short explanation about what Akka is, just so everybody has a common foundation of information to reason about. And we will look at and reason about Akka and the Java APIs and the Scala APIs too. And we will look at how domain requirements may affect how you design your code when you're building systems with Akka. And basically most of the things that we will be talking about today is based on lessons learned from building real systems with Akka.
Right, so how many of you have never ever used Akka or heard about it? Okay, I see a few hands waving. So in that case, we're just going to run through it in a nutshell. So when I mention I've been working with Akka, and people usually ask me like, oh, what kind of language is that? And I go like, no, that's no language. It's actually a toolkit for implementing reactive systems. And you all know what reactive systems are, since we heard about this in other presentations. It's implemented in Scala. And it's basically just a simple jar that you can include on your class path. So if you look at the key components in Akka, you're going to find out that there's something called actors. And actors are lightweight components, and many think that an actor is equivalent to a thread. But that's not the case, since actors can actually share a thread. But the nice thing about actors is that they're organized in a supervision hierarchy. And you can think of them more like an employee in a classical Taylor organization. So if you compare an actor to the concurrency library we have in classical Java, it would be more like the runnable. In order for actors to communicate, we have messages. And the messages are basically what contains the data and the instructions what the actors should do. In order to handle the messages, we need mailboxes. And each actor has a mailbox. And I believe the default implementation is a concurrent linked queue. And the important thing to know about message passing and mailboxes is that the order in which messages are sent is not necessarily the same as the receive order. So that means that if you have two actors, A and B, going to send a message to actor C, A may send this message before B, but when it gets to C, message B gets before message A. But as soon as it gets into the mailbox, the order is fixed. And the other thing is that actors only process one message at a time. Of course, in a big system with a lot of actors, since actors are lightweight components, one number that comes to mind is that I think they say that it takes like 2.7 million actors per gigabyte of RAM. We need something that are load balancers in the system. And there are actors that have this specific task called routers. And their duty is to pass messages to other actors according to some sort of message delivery scheme, like round robin or smallest mailbox. And of course, there's something called actor systems. And actor systems, in difference from actors, actor systems are heavyweight components. And those are responsible for creating the threads, actors, and so on. So you only want to create one actor system per logical application, so to speak. But of course, there's a lot more to Akka than this. But if you haven't played around with it yet, do so. Just browse into akka.io and check it out.
So before we move on, we would like to just define what we mean by legacy code and the term legacy in this presentation and the way we see legacy code when we talk about it outside of this presentation too. Merriam-Webster defines the word legacy as something that happened in the past or something that comes from someone in the past. And that is generally how we view the term legacy code in our industry, right? Legacy code is something that was written a long time ago, it's not maintained, it's ugly, nobody want to touch it, right? We see it a little bit different. We think it's time maybe to redefine the word legacy and legacy code. We think that the term should actually be or mean that legacy code is any code that is written in a way so that it doesn't satisfy the 4 characteristics of a reactive system. Because we really do believe that, at least from now on and into the future. And if you went to Roland's presentation this morning, you all you guys heard these characteristics, but for you who weren't there, the characteristics are responsive, scalable, event-driven, and resilient. So if you code that you write today, even if it's brand new, and it doesn't fit into this model, then we would like to call it legacy code. And that's, when we refer to legacy code in this presentation, this is what we mean. Okay, so we all know that Akka is written in Scala. And of course, you start thinking, oh, should I write my application in Scala then, since I'm going to use Akka? But we all know that both Java and Scala produce bytecode. And since Akka is just a toolkit, we can choose whichever language. But the question is, which one should we pick? So the quick answer to that one is, it depends. So in order to see how we reason, we're going to look at a quick example. All right, so assume we want to build a machine M to solve a problem P. It sounds like computer science 101, right? Where efficiency is imperative, sequential computations shall be independent, implementation of M shall be platform independent, complexity and boilerplate code shall be reduced, M's behavior shall be verifiable, and time to market is essential and risks minimized. So these are pretty normal requirements, I should say. And let's see how we should deal with this. Okay, let's talk about the first one, efficiency, since that one is imperative. First of all, is it possible to write efficient code in Java? Sure. I mean, it's not really any harder to do that in Java compared to Scala. So I wouldn't say that the efficiency requirement is language specific in this case. It's more of a design issue. So in that case, we're just going to give them 1 score each. Sequential computations shall be independent. What does that mean? Well, that basically means that we shouldn't have any memory of a previous execution in M. So it should be stateless. And is it possible to write stateless code in Java? Sure. I must say this might be easier to do with a functional language, and since Scala actually allows you to do that, it might be a little bit easier, but it's not really any problem to do that in Java. So we're still going to go with 1 point each. Okay, implementation of M shall be platform independent. Well, as we said, they both produce bytecode, they run on the JVM, and well, if you can run the JVM on whatever platform it is, sure, that will work.
Okay, complexity in boilerplate code shall be reduced. This one is one of the strong arguments for moving over to some sort of functional language, right? You can reduce that boilerplate. And we gotta admit, even though we've been doing Java for a long time, Scala actually is a little bit better than that. And I have to, of course, reserve my point here because of Java 8 might actually bring in some good, nice stuff with all the lambdas and stuff. But still, we're probably going to admit that Scala does it a little bit better. You have your case classes, and the bang operator is actually shorter than writing tell and so on. But yeah, we probably could reduce it a little bit better in Scala. So Scala is in the lead, 43. Okay, M's behavior shall be verifiable. Writing testable code, that is not language specific. It's a design decision. It really depends on how you design your system, if you can verify it or not. So in that case, it doesn't matter if you use Scala or Java. So you give them a score each, so it's 5-4. All right. Time to market is essential and risks shall be minimized. Okay, that sort of implies that there's probably a deadline, and in the projects where I'm usually at, time is not a luxury. I don't know about you guys, but it tends to be, it's a tight deadline, we have a lot of stuff to do, and if you take that, the risks into consideration, we need to look at our experience. So, Daniel, do you consider yourself as a Scala ninja?
No, maybe an apprentice, but not ninja.
Apprentice. Well, the same thing goes with me. I mean, I took a Scala class, read a book, played around with it, like you normally do. But I've been working with Java for 10 plus years, and the same thing goes to Daniel. So, with that in mind, if it's time critical and we want to minimize the risk, it would be a safer bet to actually go with Java than with Scala, even though we would like to go with Scala, right? It's kind of cool. So with that in mind, we actually, it's a tie. Okay, so how should we do it then? Well, what have we learned from this? Well, it actually turns out that it doesn't really matter which language you choose. Akka is a toolkit, a library that allows you to utilize its full potential, no matter which language you pick. Is it Java or Scala? And you should always pick the language that makes most sense. And if you look at your experience, if you have the luxury of using a new language, fine, go with it. Or if it's unsafe, play safe and try to avoid risks and go with the language you know best. Okay. So now we know that choosing language doesn't really matter, but what about Akka? We all seen these presentations where they talk about cloud and elasticity and resilience. I mean, those are the projects you want to be on, right? Where you write those fancy systems. So the question is, can we actually utilize Akka in our legacy code that we usually tend to work in? And the question is, the answer is yes. And since it is a toolkit, you need to look at the stuff in Akka and see what you can actually pull out. And one thing that you usually tend to want is your code to run faster. So you're actually interested in bringing in the parallelism from Akka. Make Akka run it on multiple cores and so on, right? The other thing you're interested in is its failure management, the supervision. In Akka, failures are first-class citizens. And that's really interesting in a parallel environment. And of course, you're interested in how can we integrate this with our legacy? Can Akka help us there? Yes, it actually can. And of course, we want to keep our system modularized, right? Since that actually helps us reuse and so on, and using a message-driven architecture like Akka enforces us to, helps us getting the code in that direction. And finally, we want to bring in Akka's abstraction model. We don't want to intermix our critical domain logic with the complexity of concurrency, like we would have done otherwise. So all of this is possible to get your code into some sort of better state.
So by now, I guess most of you understand that Akka is more or less a perfect match for doing multiple things at the same time, right? It's perfect for that. But what about in real life when you find yourself in a reactive domain and certain parts just has to be blocking, right? It always happens. Or vice versa, when you're in a legacy domain and for some reason you want to replace just a little part and make that reactive. Can you do that? Well, let's take a look. Well, in the first case, let's say we are in a reactive environment and some business requirement has forced us for some reason to make a blocking sequence of calls. Well, you can solve that with actors, but that's kind of, violating the purpose of the actors. They're not meant to do that. The advantage would be that if you already written actors for doing parallel work, then you can reuse the logic, kind of like building blocks. But the question is, what are the drawbacks when you start blocking between actors? And I will talk more about that a few slides from now, so hold that thought. And the other option is, of course, just write it with the legacy design, the good old way, the non-parallelized way. And the other scenario, when you are in a legacy environment, and okay, I can replace this part because maybe you want to make it faster because this little part we can actually parallelize. Can we replace just a little part with Akka? Well, yes, you can. Akka provides the technical means by integrating with legacy code back and forth. So that can be solved. The tricky part when you find yourself in this situation is usually how to define the boundary. So the goal here is to try to define a clear, distinct boundary from where you can go from the reactive parts to the legacy parts and back. And sometimes you need to do some refactoring in your legacy code to achieve this, but usually it's possible.
All right. So when we talk about Akka, we tend to get a question about debugging. And at first I wasn't going to bring this into this presentation, but after some thought, I was like, nah, we got to bring it in. Because many people ask this and saying like, hey, I've tried Akka, and the asynchrony in Akka makes it really hard to use the debugger. Like, what am I doing wrong? And I go like, oh, is it? And that made me think and go like, let's look at that as an example and see how are they using the debugger since they think it's hard. So in the legacy environment, we would have a scenario like this, right? We have these objects A, B to N, and in this chain of invocation, something terrible goes wrong in object N, and what do? Well, you place a breakpoint in object N. And when you do that, you're asking yourself two questions. The first one is, which value caused the crash or the strange behavior, right? And when you know that, you ask, who created it? It's sort of like the blame game. So in the legacy environment, that is fine, because the debugger gives us the call stack. You can actually see this. And if you try to do the same thing in a reactive design, we would actually place, the behavior goes weird in actor N, and we would actually try to ask ourselves the same questions again. And of course, in actor N, we could see which value that sort of broke everything. But since it's asynchronous, we wouldn't see the call stack. we wouldn't know who actually sent it. So I guess the answer to the question, am I doing it wrong? Well, no, you're using the debugger to answer the first question, but yes, you shouldn't use the debugger to find out who sent the data. And that is actually not Akka's fault. That is what we see in any event-driven architecture, right? You couldn't see who actually sent the event or message.
So supervision. In the beginning, Daniel mentioned that all actors are part of a supervision hierarchy with a boss or a supervisor that handles all the failures. And this works good when it's all in parallel. And I also talked about blocking between actors and whether or not that was a good idea or not. And it kind of goes together with the supervision part. So let's take a look at this with a simple example. In the asynchronous example, we have just a simple actor sending a message to another actor, and that actor fails for some reason. So what happens is that when the actor fails, the failure starts to propagate up through the supervision hierarchy. And then this is a very simple example, but the supervision hierarchy doesn't have to be the same as the calling order. So the caller doesn't have to be the supervisor. And in the blocking example, let's say we're making a blocking call to an actor, and the actor fails again. Well, nothing really happens. Not until one of two things happens. Either you get a timeout, because you just waited so long, or if the failing actor actually explicitly sends a failure back to the caller. Once you've done that, the failure starts to propagate up the supervision order hierarchy. Okay, so think about what implications this will have on your code. Well, since any actor can call any other actor in your system, and there's no way that the actor being called knows whether the caller is making a blocking call or not, right? So the only way to make sure that all these blocking calls actually works is to have your actors always send a failure explicitly in case something goes wrong. Okay, that's a lot of boilerplate, a lot of try catches. You don't want to do that because you write clean code, right? Well, fortunately, there's a way to solve this. And if you look in the Akka documentation, you can find a snippet of example code that you can take and tweak a little bit to fit your needs. And the end result looks a little bit like this, and it goes on. So the point is not that you should be able to read this. It's just that it's not exactly trivial. It's not super hard, but it's not trivial. And you have to take care of this stuff if you're making blocking calls. And we think that maybe this could be a good candidate to bring into the standard APIs, so you don't have to think about it. So to kind of wrap up is, if you want to make blocking calls and you want the supervision to work, then you need to just skip the actors and write the legacy code, or use actors and handle it the way I showed you, or think differently. What is it that forces you to write blocking code? Well, usually it is a business requirement that states that a process or a sequence of steps in a process needs to be done in a certain order, right? It's a sequence. But sequential doesn't imply that it has to be synchronous. So you can solve a sequential processing in an asynchronous way. You just have to switch how you see and solve problems. You have to change your mindset.
All right, so let's get into some of the embarrassment in this presentation. We're all professionals. We all know that shared mutable state is bad, especially in a multi-threaded environment, right? Nobody in here does that, except us. So the trick here is to switch your mind into not thinking sequential. So we're going to look at an example where we actually messed up and find out how we solved it. Well, first of all, we have this actor, right? And we have the properties of an actor. It has one message queue. It only processes one message at a time. Messages are processed in the order received. And an actor may choose divide and conquer to solve its task. I mean, it could call multiple actors in order to figure out how it should do it. And of course, there's something called routers. And routers are load balancers that has a lot of actors associated with it, and it's supposed to distribute its messages according to some sort of message delivery scheme, like round robin or smallest mailbox. And of course, a router can receive a lot of messages. It's nothing strange. Okay, so here we go. Consider this scenario. We have an actor with a state. So that's the red guy. And it uses divide and conquer. So it's got this big job to solve. So it sends this message to its children, so to speak, and it lets them compute it. Each message that is received from the router resets the state in this actor. And if you look at it, you can see that, well, probably new messages are going to come in during the event of computing the result from a previous message. And since this red guy actually takes care of the responses, child responses are going to get intermixed with the router messages. And since the router messages resets the state, we have a shared mutable state. Nothing strange. So how should we have done this? Well, the thing is that we all heard about the lambdas in Java 8 and the MapReduce. And this is actually the same type of problem. If you look at it, you see that now the top guy is yellow. That's the base stream. You're not allowed to modify the base stream during your MapReduce operation. And here we have a mapping to our child actors, and there's a reduction going on to the gather actor. But here we call it scatter-gather instead. So it's the same type of problem. So instead of creating a state in the actor above there, you should actually create a gather actor that's responsible for collecting the responses for that particular task. And the gather actor is never used. The gather actor collects the data and then passes the result to whoever needs it, and then it's destroyed. So the key takeaways from this is that, first of all, how did we make this mistake? Even though we really know you should never have a shared mutable state. Well, first of all, it's easy to accidentally fall back into this sequential thinking. And the fact that Akka is so fast, and you don't put your system under heavy load that often, you don't see it. So as soon as you put your system on heavy load, well, these kind of problems appear, of course. And I guess the main takeaway is avoid state. Don't use it.
State is evil.
State is evil.
So, readability. Readability of your code. Let's talk about that. Actors in Akka are untyped, and it's by design. It's intentional, which means that the method in an actor that actually handles all the messages or processes it, looks like this. It's called onReceive, and it takes a message of type object. Not more specific than that. Now this doesn't have to, but it can lead to that your code that you're writing can become, less readable. And you can also get less support from the IDE when you're navigating and trying to find, okay, where does this type of messages get processed and where does it get handled? So, usually when you start out with your little hello world actor, you kind of do this. You receive a message and you check, is this message of a type that I can handle? If it is, then you do stuff with it. And if it's not, you pass it on to the unhandled method. And the unhandled method is a method that is provided by Akka, and it's just a way of telling Akka, the Akka system, that you can handle the message that you just received. So yeah, that's a good hello world example. And then you need to handle another message type. So you add another if, right? And you do some other stuff when you get this other message. And then you realize, oh, I got to handle this third message. So what do? Well, you add yet another if statement. And I don't know about you, but this starts to look a little bit messy to me. This is a simple example. In the real world, of course, the mess is even bigger. And you start to lose readability. And Daniel and I have written this type of code a lot of times. And we thought, it's just something that we can do or do differently in order to enhance the readability of our code. So let's go through how we change step by step the way we handle messages. Not all the time, but a different approach. So it's a little bit like the evolution of our message handling approach. The first thing that we tried was to introduce we defined our own message handling method. We called it OnMessage. We could have called it anything, but we called it OnMessage. And that method took a specific message type, not an object anymore. And if we needed to handle several different message types, we would just overload that method and handle more message types. This was pretty good, because that would encapsulate and explicitly show you in the code what do we do with this specific message type, rather than having this whole if-else statement mess. What was left in the original on-receive method was basically just some logic to delegate a message type to a certain method. And to even more increase the readability, we added annotations. And these annotations didn't do anything, which is a syntactic sugar, that because in some situation might make sense to differentiate between messages that can be considered to be a request versus a response. So we added annotations to further increase the readability. And this worked pretty well for a while, but then we started to think, maybe we can take this even further. Let's see what we can do. So we introduced what we call contracts. And in this contract, we would define the behavior of the actor that we would write. In practice, it would just be a simple Java interface. And we call the methods pretty much anything we wanted to, because the behavior was defined by having methods with informative message signatures. So this made the behavior even more explicit. And it makes it really easy to read the code. You just look at the interface and you can see what behavior is defined. And it also makes it impossible for an actor not to implement all the messages that you're supposed to handle, because it's a Java interface, right? The compiler will complain if you don't implement all the methods. So this is an example of how a worker actor could look like. You implement your contract, you implement the methods. So that's also making the code really explicit. And with total freedom in method signatures naming, it was better than the version 2.0. So before, jumped ahead. We also upgraded the delegating of message types to look something like this. So this is what the original on-receive method looks like. So before we had this mess, and afterwards we would have something that looks more like this. And in our opinion, this is more readable code, because readability is probably the most important aspect of a code, because everybody needs to read code if it's supposed to survive more than a week. So contracts works pretty well as a method to explicitly define behavior in an actor, instead of just having everything in code and you have to wade through all these lines of code to understand what's happening. We're not saying that you should always use this, but if it's appropriate in your situation, then use it. It's a cool tool in your toolbox. And if you're using Scala, you can get similar support like this by using a combination of traits and case matching. So you got some stuff for free if you're using Scala.
Okay, so what about testing? Both Daniel and I are, well, we're not Scala ninjas, but we're more of TDD ninjas. And we both really like code to be testable. And so what we started out with was that, okay, let's instantiate an actor and write your unit test, like you would do. But really quickly, we realized that you cannot instantiate an actor unless it's in an actor system. So that means in your test, you need a test actor system, which the toolkit provides, that creates your actor for you. But then all suddenly, your test becomes more and more like an integration system. Integration test. And that sort of made it a little smelly. And the other thing is that it takes a little longer than your regular unit test for a POJO. So it takes a little time and effort to actually create that actor. The other thing that we started to realize was that when you communicate with actors, you send messages to them. So you need to change your mindset into, okay, I'm sending this message to it, I'm not sure what it does, and I get some sort of response back, another message. And you need to create your test sort of message-driven, right? Which makes sense. And when we did that, we started realizing that, oh, wait a minute, since we can interact with any actor on any level in our big system of actors, we could actually test a leaf, so to speak, or at any other level, like a subtree. So for that case, we could actually see how did our system behave at certain levels. And at that case, when that case happened, BDD, or behavior-driven development, were more suitable. So by writing scenarios on a particular level, you could actually capture the behavior more easily. And of course, that led to more integration tests, which everybody probably have an opinion about. But that was only for the actors. If you have other domain logic that was outside of actors, you would of course write that the regular TDD way or whatever you use. But let's look at a scenario that would bring us back to school. And the scenario could look like this: sort any sequence of numbers in increasing order. And we would state it, well, given a sequence of numbers in decreasing order, when applying the sort algorithm, the resulting sequence of numbers is in increasing order. Okay. So in order to solve that, we could actually invoke our big system on various levels and verify this. And it's also really nice that you could invoke it on the top level and say, okay, I expect this to actually give me a correct result back. I'm not sure how it did it, or which course it executed on, or nodes or whatever in my cluster, but it did it, right? And you could use like any kind of BDD framework for this, like Cucumber or Concordian or whatever, or you can use like regular JUnit and write your own DSL for it, and that would look something like this. That would basically say, given a sequence, when sorting, then the result is. And the test kit that is provided by the Akka library allows you to do that in a blocking fashion. So when you do the when sorting, you send that message to your system, and then you say, okay, I'm going to wait a certain amount of time until I get a result back from this. So that helps you to get your system, to get your tests to execute in a defined way. So in that case, you would verify whatever message you got back. All right. So what are the key takeaways from all of this? Well, first of all, it's possible to use Akka in legacy code. Even though you're working in a, well, let's say, a less attractive environment, you could actually bring out the goodies from Akka and make this beautiful piece of module code and actually get a better abstraction. And you can slowly move towards a reactive system. The second thing is that Scala, that Akka is actually Scala and Java compliant. It doesn't matter which language you choose. Of course, Akka is written in Scala, and the community tends to use Scala more than Java, at least. And that sort of makes it a little bit tricky. If you Google your special case that you're not sure how to solve, you find all these Scala examples. So if you're not too familiar with Scala, that could be a little hassle. But after a while, you get used to it, and you can say, okay, yeah, this is the way I do it in Java then. The third thing is that, you know, Akka is a toolkit, and I need to emphasize that. Akka is not all or nothing. It's a library with a lot of good stuff. And you should really pick your stuff out of it. And of course, you should stop writing legacy code and get reactive. Thank you.
There's time for a few questions. If there's anything you want to ask, yes?
You said that the messages are, well, you have no guarantee in the order of the messages. So when testing, won't you have the problem that you have randomly failing tests because, well, you provided something. This time it worked, but next time, since everything is concurrent, it can actually fail randomly.
Okay, so the question was, if we are writing tests toward a system, if you send a message to your system, will you get randomly failing tests since you cannot guarantee the message order? Did I get it correctly? Okay. Well, since your test is okay, first of all, if the same actor, if you use the example of A, B, and C again, if the same actor A sends 2 messages to C, then the order is guaranteed. So that means if your test sends 2 messages to your system, to the same actor in your system, that order will be guaranteed. If it sends to 2 different actors, then it's not guaranteed. At least I don't think so. Yeah, I mean, that would make sense. So your test you need to test the same entry point, so to speak, in your system. At least that's the way we have done it. And then you don't get the randomly failing.
So another way to put it would be like, let's say you're sending 2 messages and you expect to get a behavior for each message you send. Then you would check that, do I get those behaviors? But you might not be able to check which order do I get the behavior, right?
But of course, the result that comes back, I mean, your actor system is big. So if you send 2 messages, they get to the actor in the same order, but eventually one message may, propagate faster than the other one to depending on what your actors are doing. But then your tests need to consider, like, okay, what did I expect? So that probably depends on your test as well.
Someone else? One over here.
Have you tested any other JVM languages like Clojure or something else with Akka?
Okay, so the question was, have we tested any other languages except Java, like Clojure or Scala or any other language with Akka?
Well, personally, Scala and Java, I haven't tried Clojure or any other language together with Akka. Just Java and Scala is my experience.
Same here.
But it should work, shouldn't it?
Well, any language that produces bytecode should probably work with Akka, unless there's something special going on that Akka doesn't support. But as far as I know, yeah.
So in the same room before, there was talk about Netflix Java RX. Because we are talking about reactive programming here. So have you tried that? And can you maybe highlight some differences between, Akka and?
So the question was, have we worked any with Java RX?
Yes,
or any other reactive framework, and can we compare that to Akka? And my answer, at least, no, I haven't. What about you?
No, not unless you call the SDK, JDK compares the stuff for a framework, but no.
Right, we have one final question. Well, I guess that
one
over there. Sorry, please.
Do you know if it's possible to use Akka in an OCI environment?
Good question. The question was, do we know if you can use Akka in an OSGI environment? I don't know. That's the short answer. I never tried it. So.
Anybody in here has tried it, or?
Oh, here's some. Yes, you can.
Yes, you can.
All right. Thank you very much, Daniel and Daniel. And if you have any further questions, you can probably come down and bug them down here.